Okay, should be recording. Okay, let's begin, everyone. I'd like to mention a few things, as usual, before we start. Report 3, please take on early. Okay? I have already reduced the number of problems, provided the best solutions and best reports. That's a lot of facilitation of learning and communication of ideas, so please, reason is because the TA has to grade the reports before grading the exams, and the exams will be next week. So there's not much room for extension. There's a student who mentioned to me that there was a problem with reading the TA's comments, so I created this manual in case someone has similar problems. Okay, so this is the problem. If you read from Sakai, particularly the representative of the team that submitted the report, and if you click on the link of the report on Sakai, right, and that would bring up this PDF, and if you encounter this problem, this is like a mirror image of the comment, just like on an ambulance or police car, they often write in English so that when you look at the review mirror, then it would be right. If you encounter this problem, don't worry, because you would have to download the PDF and share with your teammates. So when you read the PDF with any of those PDF reader software, Sumatra PDF, which is a very small and nimble and can read many other formats. When I presented my PDF, it was with Sumatra PDF. The TAs use PDF Exchange to write the comments. You can also read with Nitro Reader 3. All these are free, or Adobe Reader. Okay? So there should not be any problems with that mirror image comments. And then here I provided a few screenshots: Sumatra PDF, PDF Exchange, Adobe Reader, or you can also upload to Google Drive and share with all of your teammates. And this is a screenshot from using the Google Viewer, right? So everything is fine. All right. So there should not be any problem with reading the TA's comments. I don't know what happened to Sakai. Okay, the PDF viewer. I tried this under Firefox, and I got this. All right, so that's one issue, and the other issue, for those of you who were here on Friday, and also you can look at the videos. The student who waited outside for the next class was very noisy, and at one point I put down the time here that you can look at the video. I had to go out and tell them to quiet down. So please remind me when you hear the noise that becomes really distracting. Please let me remind me to go out and ask the student to quiet down or move to another location. Yeah. So as usual, I always annotate my handwritten notes with a lot of comments after class that you can use to learn, because it's hard to compete with my own notes, right? In terms of taking down what I actually said in class. So we went through the pedestrian method to show to you how to uncouple the system of equation of motion. Casey, you missed my talk regarding the PDF. Okay, so you can view the video So this is the pedestrian way to understand how to uncouple the equation of motions, and I will not come back because there's a video that you can watch. And here you see I added a lot of words that, if you look at the videos, of course I didn't write all of these words. You know, the words in red fonts are those that I annotate after class. Okay, and I rearrange my notes. So this is a very, very nice set of notes that you should really use. You know, this is a nice resource to complement my own typeset lecture notes. Okay. So let's see, and this I'd like to mention that this is the pedestrian method to uncouple the equation of motion, right? The system of coupled equations of motion. Okay, and I'll put the comment in the previous meeting as well. And here I listed Casey for asking that question regarding the reading the TH comment. So Casey, you want to pay attention to this manual, and you can look up my video at the beginning of this class. Okay, so now I'd like to come back to at the end of the previous section. Before we move on, so I should really put section E, 53E, and that's on the model initial condition. Okay, so let me put down here and ask a critical thinking question. So we did all of this. We did all of this, and I can highlight in purple, and we obtained the uncoupled equation of motion last time, so that's purple. And what I want to provide additional, so it's already in boldface here, additional information on how to obtain the model initial conditions, right? That's the initial modal displacement and initial modal velocity. Whenever you hear the word modal, you think about the variable y1 and y2. Because d1 and d2 are the displacement in the old coordinates, whereas y1 and y2 are the displacement in the new coordinates of the normalized eigenvectors. Okay, so let me bring up my section 53E. Before we move on, okay, so 53E, and we have gone to the last page, and that's right here. And so for those of you who missed the Friday lecture, you can view the video. And even for those who were here, you can also view the video over and over and over again to get the concept, ask questions. And so here I'd like to explain to you a little more of this mystery, at least that there's no questions posed to me. Look, ask questions, get that deep learning credits. Okay. So I already said that I purposefully chose the initial displacement. This is the true displacement. This is displacement in the original coordinates to be the first normalized eigenvector, right? And then through some magic, I gave you this formula, which gives you the initial modal displacement, right? Modal displacement is y. The matrix Y contains y1 and y2, and that's phi bar transpose times m times phi bar 1. And that came out to be real simple 1, 0. No one asked any questions. Why does that? Where did it come from? Why is this formula like this? No one asked any questions. It's not active learning. Right? Remember, ask questions and you learn, you understand, and get active learning credits, and it's even better. So this is what I'd like to explain a little more here, because it's deeper than just blindly plug and chug, right? Plug in numbers and chugging is easy, but understanding the concept is more challenging and more rewarding. So here is, in fact, you have seen this formula before. Recall that we express the displacement for any time t in terms of the eigenvectors. Okay, this is the big phi bar matrix, the normalized eigenvectors, and the new coordinates, right? And this pedestrian way. Maybe let me give the class opportunity for active learning critique. What's the pedestrian way to express this expression here in terms of the individual normalized eigenvectors? Let me start with the first term. Phi1 bar times y1 t. What's the second term? Anyone? What would be the second term that you can add to this term that would be represented by that compact matrix relation? That would show understanding, right? Anderson.
Phi2 bar, y2t.
Yeah. Phi2 bar, y2t. And that was already a formula that you saw in my typeset notes. This was the starting point for projection, right? For uncoupling the two equations of motion. Okay. Without this step, nothing can be done. And without this step, then you may ask, well, why do you solve the generalized eigenvalue problem? You solve the generalized eigenvalue problem precisely because of this step. Okay? That you can express the old displacement in terms of the new eigenvectors, the normalized eigenvectors, and in terms of the new displacement y1 and y2. And you solve for y1 and y2 because that's easier to solve. Because the two equations in terms of the new displacement are uncoupled. Okay? This is the critical steps. And so, once you understand that, then it's very simple to see that if you replace t by 0, that's the initial displacement, right? And this would be equal to a known matrix, D0, that has initial displacement for, maybe let me expand so that you can follow a little in a more pedestrian way here. That is simply the column matrix that contains D1 0 and D2 0, meaning the two initial displacement, okay, in the old coordinates. And then this would be equal to the same with t replaced by 0. Right? That's it. You just replace t by 0, then you see that you have this relation now. Keep in mind, this is known, okay? This is given. That's the initial displacement. So this matrix here is given. And so what is unknown here? Active learning credits. I need to ask the question to see whether the class follows or not. Is that Taylor? What's the name?
Blake.
Blake. Okay, team 3. Okay, Black team 3. And Anderson is team 7. Okay, Black, what is unknown there?
Y0.
Yeah, so this is unknown. So this is what you want. This is like 2 equations and 2 unknowns here. Okay, so the question is how to find y, the matrix y at time t0, because you need the model initial conditions, right? We already obtained the 2 model equations. These are the uncoupled equation of motion, okay, for mode 1 and mode 2. But you need the initial model initial conditions to solve. So how do you solve this system? Let's think a few seconds. How do you solve for the matrix y at time t0? Taking advantage of the properties of the eigenvectors. What are the properties of the eigenvectors? Keep learning credit. This is very important. This is critical. What are the properties, the important properties of the eigenvectors? Somebody said something. Yeah, keep learning credit.
The orthogonality?
Orthogonality, but something more, Frank? There must be something more than just orthogonality. Maria is teammate. There's a matrix
Mass orthogonality.
with respect to the mass matrix. Yeah. But it's also orthogonal with respect to the stiffness matrix.
Yes.
Right? But the eigenvectors are only normalized with respect to the mass matrix. They are not normalized with respect to the stiffness matrix. Okay? So Maria and Frank, Frank is team 7. You see, participate. I don't care whether the answer is right or wrong. Okay, ask questions so you understand better. Right. So, and you need to review because I'm not going to go back. Okay. So orthogonality in terms of matrices, okay, would be what? Unless someone says something while I'm writing, go ahead. Okay. Think of this as I'm giving you hints here. Right, so just raise your hand and jump in and get active learning credits. Okay, maybe.
It's the transpose of C times the mass matrix times.
Yeah, very good, Maria. So this is Maria said phi bar transpose times m phi bar. Let's review. This is equal to what? Someone? Equal to what?
Was equal to 0. Right?
Yeah.
Identity matrix.
Oh, yeah.
Because these are all matrices, 2 by 2 matrices, and so you use this very important relation, and you notice this. You already have phi bar here, and there's a phi bar here. If you pre-multiply by phi bar transpose m both sides, then in a way it's like you get rid of this matrix phi bar because it becomes identity matrix. Okay, so pre-multiply both sides by phi bar transpose, then you have this known. Okay, this known matrix, that's the initial displacement in the old coordinates, and you have this on this side, and it has also been multiplied from in front. Okay, pre-multiplied means multiply from in front. All right, and that's it. Now you use orthogonality, and this is identity matrix here, and that's it. You get the result, which is simply y0, and that's why the initial modal displacement is equal to phi bar transpose m times the initial displacement. And because I know the properties of the orthogonality properties of the eigenvectors, I purposefully select D0 to be phi bar 1, right? So, and this is intentional, and the reason I chose that is because to make the initial condition very, very nicely simple, okay? So I purposefully chose D. Let me zoom out so you can see the manipulation, the mathematical manipulation. I chose D0 to be the first eigenvector. Then the result would be, right, that Y0 would be equal to, so now let me zoom in, equal to phi bar transpose M times phi bar 1, and this, you know, is equal to 1, 0. Okay? You need to be able to do that. If you're not sure, make sure that you know how to do this. Okay? Because phi bar is phi 1 bar, phi 2 bar. Okay? And there's a transpose here. Maybe I should write it down in case for you to learn. This is the same as writing maybe active learning credit. Anyone? How do you write this matrix P bar transpose? No one? This is just basic matrix theory here. Phi bar 1, phi 1 bar, phi 2 bar, but in a column, you know, you need the transpose. Okay, so if you,
isn't the transpose just like this?
okay, what, Maria?
Isn't the transpose where you put it in there? No?
Okay, okay, Maria probably meant the following. You know, recall the definition of phi bar, right? The definition of phi bar was that you put phi 1 bar and phi 2 bar side by side. Okay, like this. Okay, so when you transpose, you know, it's like when you transpose a row, then it becomes a column. But each of these has to be transposed, okay? Because this is a column matrix here. When you transpose, it becomes a row. And likewise down. Maybe a pedestrian way to understand would be as follows. If I write phi, okay. If I write A, B, meaning the two coefficients of phi 1, and then CD, okay, the two coefficients of phi 2 bar, like that, okay. Then the transpose, phi bar transpose, okay, phi bar transpose would be written like what? Active learning credit. Somebody new, okay, Matt?
Would be A, B, C, D.
A, B, C, D, yeah. Right. Kevin, you agree? Okay. Very good. And you see, if you draw the green line, then clearly AB is phi 1 bar transpose, right? This this phi 1 bar transpose here. Yeah, probably I can write like this. just rearrange this and draw a line so that we don't mix up the formula. Okay, and there's an equal sign here. Okay, so that's in detail there. All right, so now I'd like to give questions, please ask. But the next step is simple. The next step, you have everything, right? You have the initial conditions. Now the model applied force. I also chose it in such a way that you have 2, 0 and times h of t. This I already explained. And then the function h of t can take on 2 particular functions as an example, the constant, and a more difficult case is the logarithm function. So, so now we look at the case where it's constant first. The case 1, that is. Okay, case 1. So for case 1, you have the following. Okay, so this should be case 1, where h of t is equal to 1. Okay. Then you see that the this is the problem for the first mode, where you have the linear second order ODE, and on the right hand side you have 2 times h of t, and h of t is equal to 1. So you have 2, and these are the 2 initial conditions: initial displacement 1, initial velocity 0. Right? And the problem for mode 2, you have the linear second order ODE only with respect to y2, the second modal displacement. You have no applied force, so this is a homogeneous equation. And you have 2 initial conditions: initial displacement for mode 2, 0, and initial modal velocity for mode 2, 1. Okay, so 1, 0, 0. Purposefully chosen. So to illustrate the solution, and so now you need to let me zoom out. So now we focus on solving this. Right, the first step is to solve the for mode 1. Solve for the modal displacement for mode 1, meaning y1. Okay, and so this is the beginning, and this is a review here. So I'm going to go fast because this is prerequisite. You need to know this from differential equation. So the first step is to say that you decompose the solution, which is y1, that's the modal displacement for mode 1, into 2 problems, okay, 2 unknowns. The homogeneous problem, the solution for the homogeneous problem, and the solution for the particular problem. So YH means homogeneous solution for mode 1, YH1, and YP1 is particular solution for mode 1. Okay? And so you need to know what it means by homogeneous solution and particular solution, right? So that's differential equation. And I have also reviewed material in extra lectures that I posted since the beginning of the semester. So anyone who's not familiar should really get familiarized. And I'm happy to answer, again, if you have questions in class. Okay. So this is very important. Many students memorize, and that's not a good idea. Okay. It's not a good idea to memorize. You have to understand why you do this.
All right.
Okay, so homogeneous solution means that you rewrite exactly the same differential equation, but no right-hand side. That's why it's called homogeneous. And the equivalent to homogeneous in the language of vibration is free. Free vibration, meaning no excitation. And you saw the undamped free vibration, That's what it means. That's the parallelism between vibration and differential equation. Right? So in the language of differential equation, this word is used. So now you see, for the particular solution, you actually put in the actual excitation, and in this case, because the function h of t is a constant, so the excitation is just a constant function equal to 2. Okay? But otherwise, you see the equations, at least the coefficients are the same, but not the unknown function, right? This is written as yh1, that's the homogeneous solution, and this is written as yb1, that's the particular solution, and these are not the same. And so for the homogeneous solution, when you solve the homogeneous solution, you go down here, then you would introduce this trial solution that was handed to us by Euler. It's called trial solution because at this stage it's an assumption. Jackie?
Do we have to do that on the test?
Okay, the question is, do we have to do that on the test? If I say write everything in details, yeah, please do that. Yeah, don't just copy the formula and give the solution. Because you want to show that you know the material and you have the practice problem ahead already. So yeah, please. Because you want to, like I said, the test is not really just to get the answer, or even in your report, the goal is really not to get the answer. No. The goal is to understand the procedure, the process of arriving at the solution. That's learning, understanding, rather than just plugging the formula. Did I answer your question? I always emphasize understanding, not plug and chug. I hope you agree. And so if you introduce this trial solution into the differential equation, then you get the characteristic equation. And when you solve for the characteristic equation, you get the roots. Okay? And that would provide you the solution, the homogeneous solution. And in this case, it turns out that when you solve this characteristic equation, you have a pair of complex conjugate solution. Now, this is by design. I actually start from here and I go up. Okay, I purposefully choose for the mode 1 equation to fall into case 3. Remember, case 3 is what? Active learning credit. There are 3 cases, right, of the vibration of single degree freedom system. Casey? Underdamped, yeah. Underdamped means that you have oscillation, right? If it's overdamped, do you have oscillation? Somebody?
Yes.
If it's overdamped, Kai?
Yes.
If it's overdamped, you have oscillation?
No, it's flat.
No, yeah. It just go down like this, okay? And critically damped, also no oscillation. So Kyle is team 6, and KZ is team 2.
What are the meanings of the 3 roots again?
Okay.
If they're
yeah,
double.
I'll be with you,
Okay.
Maria. Very good. Let me note down KZ. What is the meaning
There's the
of
double real root. There's the 2
Oh yeah,
different
okay.
roots. And
So
there's the
Maria
complex.
asked to review the 3 cases. When you solve for the discriminant, right? You find the discriminant, and the discriminant would have 3 cases, whether it's greater than 0, equal 0, or less than 0, right? When the discriminant is greater than 0, then you have 2 real roots. When the discriminant delta, like that delta equal to 0, then you have the double real root, delta. That's d squared minus 4ac, right? I mean, if you this is quadratic equation, so let me not rewriting this because I already wrote it in the previous section. So all I want to say that this is a quick review. You have okay, so this is the case where the discriminant is negative, so the square root is complex, so that's why you have the complex conjugate pair. Okay, and this is when you have oscillations. All right. So if there's no problem with this, and here I also indicate that you can use Wolfram alpha to verify the solution. So then your homogeneous solution would have this form. Okay. Let me put on the mask so that it's not overwhelming. Okay. You have the two solutions which I denote lambda 1, 1 and lambda 1, 2, right? The first index is related to mode 1, and the second index is the second index is the order of the two roots. We have lambda 1, 1 and lambda 1, 2, right? There are two roots, and the first index 1 is mode 1. So you combine the two solution. Solution means exponential of lambda 1, 1 t and exponential of lambda 1, 2 t. And remember, lambda 1, 1 and lambda 1, 2 are complex numbers. Okay, and so p11 and p12 are the coefficients to be determined. And so this is a complex valued function. At first sight, if you use Euler's formula, right? And I have already reviewed to you Euler's formula that led to the most beautiful formula in mathematics. And I also indicated the section in which you can convert complex valued function into real valued function. Okay, where you see cosine and sine, because vibration you expect the result to be real valued function. Not complex value function. So here you see exponential and then cosine and sine. All these and the coefficients Q11 and Q12 are all real numbers. And these two coefficients, how do you determine the two coefficients Q11 and Q12? Someone give learning credit. These are two free parameters that you need to determine, right? How do you determine these two free parameters? This is also a review of differential equations here. Okay, so before that, you need to find the particular solution. The answer is you need to use the initial conditions. But you can only use the initial conditions after you have added the particular solution. And the particular solution for this particular problem, for this special problem, is equal to 1/2 y. Would someone explain to the class why for active learning credits? Let's zoom out. Maybe instead of zooming in and out, let me bring up one more windows here. Put it aside. And so to remind you of the problem for the particular solution. This one here. You need to solve this equation for the particular solution. So the question is, why is the particular solution is equal to 1/2? Someone? Why is YP 1 of T is equal to 1/2? one? No one? Frank?
Are y prime and y double prime zeros?
Yeah, just plug it in. Second derivative is 0, first derivative is 0, 4 divided by 2 is 2. Check. That's the solution. This is an easy problem, really, but it's getting more complex later. This is a differential equation here. Okay, so that's the reason why over here you see that I wrote the particular solution is 1/2, right? And so now let's move forward. Now you combine, okay? You combine both the homogeneous solution and the particular solution. Homogeneous solution is this term here, which you saw before, right? That has the exponential, rho 1, and then there's the cosine term, sine term, and the two parameters to be determined, q11 and q12. And 1/2 is the particular solution. Only after you combine the homogeneous solution and the particular solution, that you would try to satisfy the initial conditions, the model initial conditions, to find q11 and q12. Only after you find q11 and q12 that you would completely solve the first, the mode 1 problem. Okay? And so that is known here. So you have this expression, and the two unknowns are q11 and q12. Okay?
So our particular solution was just achieved by kind of like guessing, really, like looking at the equation and then.
Yeah. So Devine asked the particular solution is achieved by guessing. You can say that. Yeah.
Okay.
It is so simple that you can guess. Yes. And in the book by Crazy or any other books, they give you a table. You know, if the excitation is sine or cosine, I think we did review that. Then the particular solution, the guess is that you must have both sine and cosine, right? Because when you differentiate, if the excitation is sine, you will have cosine popping out, and then you take the second derivative. So that's why you need to have both terms. So please review that. It's in my extra lectures also. So here you take the derivative, right, of the total solution. You know, so you have all of these terms. Okay, the 1/2 disappear, so that's a constant. So you have the first term comes from the differentiation of the exponential. That's why you have rho 1 coming out. Same factor, cosine and sine. And then the second term is the differentiation of the term in square brackets. Okay? And you need to also differentiate the one more time, right? Because you need to replace the solution into the differential equation, right? So you need to differentiate once more, and that would be, let me zoom out so you can see the big picture. Yeah, so here, okay, so here let me take it back. Right now you have already y1 and y1 prime, so all you need is just to set the time t equal to 0. Okay? So here you set time t equal to 0, and we already obtained the model initial displacement, right? And that is y1 at time 0 equal to 1. Then you can solve for one coefficient q11, right? So just replace t equal to 0 in the expression for y1, and you get the exponential is equal to 1. Cosine of 0 is 1. That's why you have q11, and and then sine of 0 is 0, and then 1/2 is the constant out there. Okay, so you can find q11. Okay. And then you need to find q12, and for that You can use zoom in. You can use the initial velocity. So y1 prime times 0 equal to, just replace t equal to 0 and set the value to 0. That gives you another equation to solve for Q12. Q11 is known by now. So, and rho 1 and omega 1 tilde are known. So therefore, you can get the result. Dylan.
I'm sorry, when you, I know it's like a page up, but when you said that the first and second.
Let me ask this guy. Hey guys, could you please quiet down? There's a camera here. Pick up your noise. Okay, thank you. Yes.
When he had said that the first and second derivatives were going to 0, what were they representing again? How did they go to 0?
No, they are not 0. You replace the time t. The time t equal to 0, and you can see.
Okay.
Okay, in the expression for
Okay, so then at time
the
t
0, yeah. Let's
okay.
zoom out so you see the big picture. Right here, Milan. Okay, so here, that's, you know, so we yeah, this is good. So you have this expression, right? This is the modal displacement, and so you just replace t equal to 0. Okay. Because you have the value of the modal displacement at time t equal to 0, and that's equal to 1 there. And so you just take this expression, set t equal to 0, then you have one equation for one unknown here, just because the sign of 0 is 0. But in principle, you would have two equations for two unknowns, because the first equation comes from the modal displacement, and second equation comes from the modal velocity at time t equal to 0. Okay. That's why you need to differentiate to get the modal velocity for all time t, and then set time t equal to 0, because you know the value of the modal velocity right here. Y1 prime at time t equal to 0 equal y1 prime at t equal to 0 is equal to 0. Right? Two equations, two unknowns in principle. You can solve for these two coefficients, and finally, this is the result here. This is the complete result, the modal displacement that satisfies the modal initial conditions. Lecture summary, we can continue next. Thank you, please. And Dylan, I'll give you active learning credits here, and that's team 3. Team 3.